we're going to do part E now. Suppose the snow machine is turned off at time t equals 10. Write but do not solve an equation that could be solved to find the time t equals k when the snow would all be melted. Generally, they do not have us solve these equations because they're very, very difficult to solve, and we have not learned how to do that. So just leave it alone after you find the equation. What's going on here is that we're going to have a certain volume of snow that is on the slope, and after k hours, well, k minus 10 hours, we're going to have a lot of melting going on. So the volume that is melted, which is going to be the integral of m of t dt, that melting is going to be happening between 10 and k hours, right? I know that there's more melting going on before that, but that is going to be incorporated into the volume of snow that's on the slope at t equals 10. We have an equation, or an expression, I guess, for volume of the snow on the slope at t equals 10, and that is going to be just like A of 10. Okay, we know that A of t is the total volume. We came up with that a while back. And we could use the integral of y3, math 9, 0 to 10 of y3 dx to help us figure out that we would get 133.159 would be the difference between when we started and when we ended. If we add the 50 to that, that's like our starting value, we end up with 183.183. Because this is the snow that accumulates between 0 and 10, and we didn't feed into our calculator the fact that there were 50 to start with. Okay, so this needs to be 183.193 equals that integral. So that's literally it. If we subtract this integral from both sides, we get 0 equals the integral from 10 to k of m of t dt. So you might see it like this equals that, or 0 equals this minus that, kind of whatever. All right, we are done with that problem. We're moving on to this page, which is a couple pages ahead. It's on 523. We have a particle that is moving along a straight path. This velocity of the particle is valid between 0 and 30. Looks like seconds. There's no label there. And that's shown in the table. Velocity is at a maximum at t equals 20 seconds. They told us that, so it's probably important somewhere. Answer the questions that follow. Fantastic. So first off, use the midpoints of 5 subintervals of equal length to approximate the value of this integral, and then explain the meaning of that value. Okay, notice that 30 is the difference between 0 and 30. So this right here is 1 over b minus a. So this is not finding the difference between our positions. I mean, this part does. This finds the distance. But then we divide it by time again. And distance divided by time is velocity. So what we're finding is the average velocity between our two endpoints. This goes back to page 520. Okay. All of these questions are written up here at the top, just like, whatever, they're written at the top. A, using midpoints of 5 subintervals. I'm going to go ahead and explain the meaning right now. The average velocity from t equals 0 to t equals 30 seconds is something meters per second. Boom. Okay, midpoint of 5 subintervals of equal length. Okay. I'm going to find that integral 0 to 30 of v of t dt. we're going to multiply it times 1 over 30. So this is 1 over 30 times, and then we can figure out how wide our subintervals are. We need 5 of them. 0 to 30, that's 30, and then divide that by 5, and we get 6. So our subintervals should have a width of 6. And 1, 2, 3, 4, 5. Perfect, we got it. So I'm going to go ahead and put 6 down here as our width. And then we're adding together 5 heights. 1, 2, 3, 4, 5. Beautiful. Okay, our heights are 7.5 because that's the midway between 0 and 6. 7.5, 12.5, 13.5, 21 will be 14, and 27 gets us 13. Okay, if you add together all of those numbers, multiply by 6 and divide by 30, what are we gonna get? 7.5 plus 12.5, 13.5, 14, and 13 is, I got 60.5. That all looks good. Times 6 over 30 is 12.1. Okay, so 12.1 is our average velocity. B, find the average acceleration of the particle over the interval from t equals 6 to 18. B, average acceleration equals the slope of velocity. So it's going to be the velocity at a certain time minus velocity at a certain time over, and then we subtract our numbers on the bottom. Okay. V of, what were our numbers? 6 and 18. So 18, 6, 18, 6. At 18, we have 14.1. Minus 6 is 10.1. That subtracts nicely to get 4. 18 minus 6 is 12. This is 0.3. Repeating, or 1/3. Acceleration is the slope of velocity. Velocity was meters per second, and then we're dividing by a number of seconds, so this is meters per second squared. Cool. C, find an approximation of v prime of 6. That is an approximation of a slope. So we are going to use this exact same formula. We're just getting close to 6. So v prime of 6 is approximately the average acceleration. Okay, v prime of 6 is the instantaneous acceleration at t equals 6, but we don't know instantaneous acceleration. We're not given like a table of accelerations, and we're not given an actual like function that we can deal with. So we do what we can with what we've got. So this is around t equals 6. So we're going to pick t equals 9 and t equals 3. So that should be v of 9 is 13, v of 3 is 7.5. All of that is over 6. That was a coincidence that that was 6. 13 minus 7.5 is 5.5. And divide that by 6. We get 0.91 and then 6 repeating, so 7 meters per second squared is our approximation. Explain what this value represents and state, providing justification if the speed of the particle is increasing or decreasing at t equals 6. We talked about how it's the average acceleration. Justify if the speed of the particle is increasing or decreasing. Okay, so remember that speed is the absolute value of velocity right? If your velocity and your acceleration have the same signs, I'm pointing at v prime, but if your velocity and acceleration have the same signs, then you will have an increase in speed. Our velocity at t equals 6 is positive. Our acceleration at t equals 6 is positive. So you would say since acceleration and velocity have the same signs, at t equals 6, the particle is speeding up. Or you could say the speed is increasing. Cool. D, find that integral using a left-hand approximation of two subintervals of equal length. Two subintervals of equal length, just from 3 to 9. Okay, so we're not going very far. We're just going here to here. I'm going to erase the rectangles that I've got on here. We're going from 3 to 9 with a left-hand subinterval. So our widths of our rectangles from 3 to 6 is 3, 6 to 9 is 3, and then our heights are 7.5 and 10.1. Okay, that is very small. We don't do that very often. Integral 3 to 9 of v of t dt is going to be approximately, not actually equal to, the width was 3, the heights are 7.5 and 10.1. That'd be 17.6 times 3 is 52.8. We just took the integral of velocity, so that was meters per second. Integral of velocity is going to be meters, because it's like the position. Then use this value to find the position of the particle at t equals 3 seconds if the position at t equals 9 seconds is 60 meters. Okay, we know that our integral represents position at 9 minus position at 3. All right, this thing equals p of 9 minus p of 3. Okay, fundamental theorem of calculus. Usually this is on the left side, this is on the right side. We know that p of 9 is, where'd that go? 60. So 60 minus p of 3 equals 52.8. I will add 52.8 to both sides. No, subtract. Good morning. Minus 52.8. And add p of 3 to both sides. So we end up with, looks like 7.2 equals p of 3. Yep, that looks good. This is meters. So we are done with that. Fantastic.